Hi, I'm Steve LaCava. Today we're going to be presenting simulation and analysis of optical fluid effects. This work has been presented by a number of people who are listed here on the slide, and they have all contributed to the research you're about to see today. Right, so looking at some of the effects, such as aero-optics and stop analysis, and those associated with the optical effects of fluid, it's a very complex problem, and we wanted to find out some of the reasons why in the past people have done these with kind of a test and break methodology, where they simply did experimentation as opposed to simulations. So to understand this and understand how simulation could help in this situation, we wanted to analyze all of the physics that were involved and kind of break down the problem. So I went ahead and took a look at an aero-optic effect problem. And we wanted to look at it from two standpoints. One from an observer looking at a craft, and then one from the observer on the craft's perspective. So in this scenario here, we have the craft in that upper left corner, and we went ahead and put a window in that system and an optical system behind that. Looking at the window, and we wanted to look at how the pressures and things would change as this aircraft were flying. As the aircraft is moving at higher and higher speeds, pressure is going to build up on that window. That pressure is going to cause deformation to the window itself. In addition to that, it's going to cause a thermal index change from the heat buildup in the window itself as well. On top of that, the entire vehicle is heating, which is going to cause the mounts and things to thermally expand, which is going to cause deformation as well as rigid body motions to all of the optics. And the optics themselves are going to exhibit a thermal index change, which will be non-uniform in nature as well in the system. In addition to that, as we increase higher and higher speeds, that air in front of the window is going to become turbulent. You get going fast enough, you start to see shock waves. You get going even faster in the system, and you begin to get separation of molecules. You go even faster, you get ionization and plasmatic effects. All of these are problems from an optical standpoint. And all of these are issues that we really need to deal with. Taking a look at all of those scenarios, it's easy to see why people may have thought in the past that this was difficult to simulate. However, the good news is we can actually simulate these elements now. So to do this, we start off just as you would with any system. We go ahead and take our CAD model of the system, figure out where the optical system is going to be in place, figure out what the mounts are going to be, etc., and put those into our systems. Then we wanted to go ahead and look at two scenarios, as I mentioned earlier. So the first scenario is going to be what happens from an observer looking at the vehicle. So imagine a high-speed vehicle being observed from a third party. What would that look like, and how could we analyze that? So to do that, we went ahead and leveraged tools like STK to be able to do our orbital motions of both the aircraft as well as the orbital motion of a satellite in this scenario. We then leveraged Ansys Fluent, which is our CFD solver, to figure out all of the heats and pressures that are on that vehicle. You can even look at things like ablation of the materials of the vehicle itself, as how it's changing shape. All of that is going to contribute to the thermal signature that an EOIR sensor is going to pick up from that vehicle by the third party. So in this case, we're going ahead and kind of analyzing that scenario. And you can see the satellite coming into the picture. The aircraft itself is going to be moving on a trajectory on the Earth itself, and then the Earth is also rotating and moving within its orbit as well. At some point, enough solar flux is going to hit that object where you're going to actually get the albedo of the Earth to wash out the vehicle. So in that upper left corner, you see that small dot? That is our aircraft. Then the Earth itself is going to begin to change in temperature, which is going to change what we see on the EOIR sensor. And eventually those two are going to match in intensity. So the albedo of the Earth is actually going to wash out that vehicle. And that's going to basically create kind of a saturation point for us. However, if we were to take this a step further and apply some optics to the system, perhaps that satellite had a filter wheel attached to it, where we could actually change the polarizing filters that were on the image. At that point, what we would be able to look at is the difference in polarization between the scattered light from the Earth and that scattered light from the vehicle that's in flight, because they're not going to be polarized the same way. That would actually allow us to basically get a false color image where we could see a dot continually moving on that backdrop of the Earth, even past the point of just pure intensity saturation. So then the more difficult of the questions becomes, what does the vehicle itself actually experience, and how does that look for us? So to solve that problem, we have to look at a number of different tools. We have to start at the mission level with the system. So we'll go ahead and at the mission level, begin to take a look at what's happening with our system. So we're going to look at the trajectory of the aircraft. That's going to then define the strata layer that the aircraft is flying in, which will actually define the species of gases that the vehicle is flying through. All of that's going to be fed into a CFD tool. For the mission stuff, we're dealing with STK. On the fluid side, we're using Ansys Fluent, and we're going to go ahead and use all of those elements as our input parameters. So we're going to go ahead and look at things like the compression of those gases, the thermal expansion, the interaction, the shock waves, any kind of separation or ionization that might occur. All those variables are going to be in play in the fluid analysis as we're trying to define the flow field. All of that is then going to wind up defining the pressure and temperatures upon the vehicle, the window, etc. That is all going to become the initial conditions for our FEA analysis. So we're going to go from our computational fluid dynamics to our finite element analysis. For that, we're going to leverage Ansys Mechanical. And at that point, we're going to look at things like mechanical deformation, rigid body motion, tilts, decenters, etc., as well as the thermal lensing effects. The actual index of refraction will change as a function of temperature and pressure in those systems. And we want to be able to define all of that. And then finally, we want to bring all this back into the optics world. And we want to look at two things with this. We want to look at not only that nominal system that we'd started with, but we want to look at leveraging something called STOP analysis, which is structural thermal optical performance. It's a traditional analysis that you're looking at with all of the physical structures, the lenses, the mirrors, the windows, etc. in the system. But we want to go a step further. We also want to look at the aero-optical effects. We want to look at that volume of gas in front of the window as well. And we want to put those two things together to give ourselves a full picture. And for that, we're introducing a new term. We call it SOFT analysis. It stands for Structural Optical Fluids Thermal. And that's going to allow us to look at the full picture of this entire system. So let's take a look at how we actually do that. In this case, we're going to start with a nacelle or a pod under the wing of an aircraft. And we want to look at that volume of gas that you see in the blue in front of that nacelle. We also want to look at the optics themselves inside of the system. In this image, we do not show the mounts. However, the system does have mounts for the FEA analysis portion. So we start off the system just like we would any system. We start off with our nominal optical design. We're going to specify things like wavelengths, fields, apertures, any kind of coatings and materials in the system are all going to be defined and brought in from an optical standpoint. The other nice thing is we have the ability to optimize around pretty much any parameter we choose, whether it be MTF, wavefront, point spread function, etc. in the system. We can also look at aberrations. What you're looking at in that lower left is a Seidel diagram that actually shows you the aberrations surface by surface through the system. Every time we introduce an optical element, we may correct an aberration from a previous element, but we introduce one of our own in the process. The goal is to get that column that says sum to the right of that Seidel diagram to be as flat as possible. We hope that the number of optics we put into the system all balance one another and cancel each other out. And then the next piece of the puzzle is what about tolerancing? We're going to put this into a vehicle, as we talked about it, and put it into mounts. Let's assume, for example, just to keep it simple, that first doublet that you see in the system on the left, upper left there, is going to be glued into place. What happens if it's glued incorrectly? What if it's decentered, tilted, etc.? That second section there, that second doublet that's highlighted might be the compensator in that case. We might allow that to actually move to some degree or tilt or rotate. In which case, we can actually go ahead and run a Monte Carlo on the system that if you were to produce X number of these a year, how many would fall within your tolerance levels? And all of that can be built out. We can even do things like glass substitution for your material classes, and of course, export all of this for optomechanical design. On the optomechanical side, this is where we really see the value of a one Ansys solution, where everything is under a single umbrella. Because these step mounts that you're seeing here in the dark blue on that lens, those are very difficult to make in an optical tool, but they're very easy to make in a CAD tool. The lens itself, very easy to make in an optical tool, very difficult to get complex curvatures in a CAD tool. However, putting these two tools together and specifying the distance between them is nominal in nature allows us to bring this into FEA as if it were a monolithic piece of glass. So we're leveraging the best of each of the tools' capabilities and blending them. We then move into our fluid solver. In this case, again, Ansys Fluent for this. We're going to look at the flow field. We're going to look at all of the stresses, pressures, temperatures on the system so that we can feed all of that to our mechanical for our stop analysis. We bring that in for the stop analysis, and we're going to go ahead and do our structural and thermal deformations at this point. We can also leverage thermal desktop if we need it for thermal, especially for things like satellites and orbital systems, or we can use Ansys Mechanical for both of those elements. The other nice thing with leveraging Ansys Mechanical is we have an ACT script that was created for it, which allows us to export that data in a format that Optics Studio will actually recognize it in. You can go ahead and specify the time steps, where you want it saved, what you want it named, etc. And it's as simple as just clicking on either the part tree, you right-click on the part tree or the part itself, and you simply click Export to Star. And that will allow you to bring it into the system. Once we bring that into the system, it's going to be brought into the system as a point cloud. That point cloud is going to be the vertices of each of the nodal location of the vertices of each of the meshes in that system. is what's going to make that point cloud. The nice thing is that you can leverage mesh control. So our point cloud can actually be dense in some areas, sparse in other areas, thereby allowing you to have the fidelity you need in the areas you care about while still being computationally efficient. In addition to that, if symmetry does exist in your system, you can actually leverage our symmetry tool, which will further reduce computational time. And of course, when symmetry doesn't exist, you can still bring in an asymmetrical system. That will allow you, regardless if it's symmetrical or not, to go from your nominal system, bring in all your FEA data, and then look at the degradation to that system in the original metrics that were used for the nominal design. So in our case, of that nacelle under the wing of the aircraft, which you're seeing in the upper left there, we went ahead and looked at the point cloud that came from our stop analysis right there on the left in the lower image. That's the point cloud on each of the substrates, each of the lenses. And then to the right of that, we went ahead and looked at a point spread function and a wavefront map were the two metrics we chose. However, you could have chosen any of the metrics within Optics Studio. And then we looked at the nominal, the structural, and the thermal. And as you can see, the nominal looks pretty clean. That point size is pretty small. Wavefront map, while not perfect, is probably as close to perfect as this system is going to get. Structural gets a little bit worse. So then we bring in the thermal, and you can see that point size is very asymmetrical, as is the wavefront map in the system. But that's not where we stop. The real power of this is the ability to replace a lot of testing, prototyping, tooling, etc. So what you're looking at in that bar chart at the bottom there, that's actually an image that came out of our optical tool, Optics Studio. And it's showing you surface by surface, the structural and the thermal components, and which is contributing the most to the change in spot size. Now, in this system, we expected the first lens to see the greatest thermal and structural deformations to the system. However, you notice that in terms of optical aberration, the last two surfaces, number 7 and 8, which represent the front and the back of that last lens, is actually causing the greatest optical aberration, even though it's the most protected. When we go back up to that image in the top there, which comes from Ansys Mechanical, we can see why. So even though the forces in terms of the intensity levels, those arrows are blue, not red in this case, they are weaker than that front lens. They're pushing against the direction of curvature of that lens because that lens was thin and made out of an inferior material. So it's actually being bent against its direction of curvature in this case, which is causing a greater optical aberration despite it being the most protected. Catching this before we ever flew it, prototyped it, or built it allows for the engineers to design around these types of solutions and really build the things out in a better way, moving that simulation to the left of your system. Now taking a look at the aero-optical effects. We want to look at what happens when we look through a turbulent flow field. So you're looking through that system and you're creating an aberrated wavefront. And we want to be able to find a way to model that. So to leverage that, we go back to Fluent. And you can see there in that image in the bottom, we actually did leverage mesh control to have a dense mesh in an area we cared about, sparse mesh in the other areas. We can even use something called named regions to carve out a section that's of optical interest to us so that we're only importing the areas that are of concern. The other nice thing that we have with everything being under one umbrella and being part of one Ansys is we have the ability to update multiple tools simultaneously for an end goal. In this case, what you're looking at is the optical path length and the optical path difference. We're essentially able to look at phase, not in an optical tool, but in a CFD tool. This is Ansys Fluent, allowing us to look at a transient flow and the optical path length and optical path difference in those systems. So we're actually providing optical tools into the fluid system and fluids elements into the optical system. And once we go ahead and export all of that data, that image in the upper right there, you see our nacelle, and you see the densities changing. So as those pressures build up, the density of the air is different in each of those. That's going to wind up, the density and pressure is going to wind up deciding what the index of refraction is because it's temperature and density dependent. When you look at that image, an optical engineer would tell you it looks a lot like a grin lens, which means we can solve for it. So we just need to get the index of refraction out. And to do that, we're leveraging something called the custom field function inside of Fluent. The powerful thing of this is you can use any equation you like. In the case of the aero-optical effect, we chose Gladstone-Dale for this. But you could have used something like Lorentz-Lorenz if you had polarization that was dominant, or you could leverage even something that's a custom equation if you're doing something like, let's say, making a proprietary fluid for a liquid lens. In any event, that will all be able to be exported and brought into the system. We bring it in just like we do the stop analysis, so it comes in as a point cloud, very similarly. It's a volumetric point cloud in this case. And then we've added more analysis tools to our optical solver. So what you're looking at there in that bottom image is a heat map, and it's showing you the index of refraction of the volume of gas in front of the window in front of that nacelle in that system. Red is higher index, blue is lower index in the system. So you can see that we have a very asymmetrical setup here of the difference in the index of refraction of the light, and then we can ray trace through this system. The powerful thing of that is it gives us not only the optical path length and path difference, but it gives us refraction effects. So we can actually look at things like distortion. So we can go ahead and look at this image test plate here, and you can see the image on the right is a little bit blurry along the edges of the numbers and those straight lines, where the image on the left is much more sharp. And that's in our nominal system or nominal design that we benchmarked to. And then the real power is we have the ability to turn these things on and off at will. So we can look at things like the thermal and structural separate, the aero-optic separate, and put it all together. So we can look at the nominal, the structural, the thermal and structural together. And then we can also look at that with the aero-optics, and then the aero-optics and the stop analysis combined in the system and see the effects. We've also expanded some of the analytic tools. So going beyond just creating pretty pictures, we can actually give some values to this. So that system that you looked at earlier that showed the structural and thermal and the stop analysis, we've taken it a step further. We can now break down structural to include rigid body motion or not include rigid body motion. We can look at the thermal, and we can now look at the direct index. So we can look at what the effect of just the index of refraction of a volumetric point cloud has on the system as well. And all of these can be turned on and off element by element within your system to really allow you to interrogate the light. Finally, once we make those changes, just like we did in the stop analysis, we can go ahead and look at different material classes. And we can look at how those materials are affected by temperature and thereby select better materials for future analysis. So far what we've looked at is a very linear process. The process we took you through kind of starts on the left there with the optical design, moves into optomechanical, moves into fluids, moves from there into mechanical and FEA analysis, and then comes back into the optical solver. In the future, however, this is going to be more like kids with building blocks. We're going to allow people to select the solvers. So you might leverage, say, thermal desktop or mechanical for the thermal. You might use mechanical for the structural. You might use Fluent for the fluid solver. You may need some combination of bits and pieces of these. You might even need different optical solvers. You might want to use like Speos for non-sequential and Zmax for the sequential portion of it. And the nice thing is all of these are going to kind of be able to be intermingled, and they're going to be dynamically linked, meaning we can actually look at transients and dependencies between these systems as we're solving them, which is really going to give us the next level of this kind of workflow with the system and make it more versatile, which allows us to solve a lot of different solutions. So we're actually able to solve things like localized weather conditions for ground-based telescopes or adaptive optics systems, pretty much any system where you have stress and thermally induced elements. Underwater examples, whether it be laser communications or bathynomy, which is effectively underwater LiDAR to get high resolution elements around, like, say, bridge footings or something of that nature. Convection of high-powered beams, when you're looking at, like, say, a cutting laser or additive manufacturing, that heat will build up in the lens. It's not perfectly transmitting, and that's going to actually radiate, causing basically a turbulent flow or convection currents between the lenses. That acts like an optical element in the system that was unintended. We can actually model those elements now and solve for them. Atmospheric effects, whether we're talking the moon of Titan or Earth itself, you're going to be looking at atmospheric effects, and those need to be addressed as well. And then my personal favorite, when you get into extreme high-powered laser systems, you actually wind up with material phase changes. So like petawatt level lasers that they use for fusion reactors and things of that nature, they use basically a piece of fused silica, and they allow a lower energy beam to pass through it, the pilot beam that passes through it. The on-target beam hits that glass, that fused silica, vaporizes the top layer, turning it into a highly reflective plasma, which then allows the light to bounce through to the target location. Those types of effects in the past have only been analyzed in a laboratory scenario. We can actually now model those effects and simulate them ahead of time to find out how they're going to behave in the system. And this is the real power of bringing all of this under the one Ansys umbrella, because now we can actually solve a number of different types of problems end to end in that solution and really bring everything together for our customers. And with that, go ahead and leave you guys with any thoughts that you may have. Go ahead and reach out to us with. Thank you for your time.
I'm still amazed at what on this bus and no one's driving it.
There is no driver here. And more than 90% of the accidents are caused by human error. This can be prevented if we really let the car drive itself. And this is where simulation comes in critically.